Today, we're delighted to introduce Felix Otto. Professor Otto has been a director at the Max Planck Institute for Mathematics and the Sciences in Leipzig since 2010. Earlier, he was a postdoc at the Courant Institute and the Center for Nonlinear Analysis at Carnegie Mellon, and professor at the University of California, Santa Barbara. At the Department of Applied Mathematics at the University of Bonn, he was the founding director of the Hausdorff Center for Mathematics, serving as its director from 2006 to 2009. His main expertise is in the applied analysis of partial differential equations and the calculus of variations. He has worked on gradient flow structures of dissipative evolution equations, on pattern formation in ferromagnetics, and on stochastic homogenization, for example. He was awarded the Max Planck Research Prize, the Leibniz Prize of the German Science Foundation, and the Golatz Prize of the CIC-IAM. Now, this series is co-sponsored by the SIAM Journal on Mathematical Analysis, so I would like to point out that he is the co-author of its most popular paper. Please join me in welcoming Professor Otto, whose title is The Thresholding Scheme for Mean Curvature Flow and de Giorgi's Idea for Gradient Flows. Felix.
Thank you, David, for this kind introduction. Can you hear me? Okay.
I hear you, yes.
So indeed, there is also a relation between the SIAM paper with David Kinderlehrer and Rich Jordan, which was just mentioned, and this talk. So, but this talk is based on joint work with Selim Ezedoglu, who's at the University of Michigan in Ann Arbor. And we started this when both of us were staying for a month at the IMA in Minneapolis, and about 10 years ago. And then later on, Tim Laux was PhD student here in Leipzig, and now is has a professor position, kind of junior professor position in Bonn, joined in about 5 years ago. So that's joint work with both of them. So the topic is a little bit of a mixed topic, and which touches upon several areas of mathematics. So it's about mean curvature flow, so flow of a surface by its mean curvature. So that's geometric analysis, but it's motivated by material science, more precisely by the growth of grains in a polycrystalline material, in a metal. And but it appeals to a little bit of abstract analysis, so analysis of metric spaces and ideas of Ennio de Giorgi in that context to deal with gradient flows. But in a certain sense, the main object is an object from scientific computing, namely kind of a numerical scheme, a very successful numerical scheme for mean curvature flow. So, I hope that I will get to all of these subjects in some order, and everybody of you can take it, something out of one of the four things. I mean, hopefully more than one. So that's the start. So let me tell you what the flow by mean curvature is. I'm sure many of you have heard of it. So what's mean curvature? Let's stay with curved surfaces. So in kind of two-dimensional objects in three-dimensional space. So in this case, the mean curvature is the sum of the principal curvatures, the principal curvature directions, and typically it's denoted by h. So for instance, for this dumbbell-shaped figure, the curvature changes, the mean curvature changes in sign, and I will normalize it in such a way that it's positive in these convex ends, and it's negative in the wasp type region in the middle. So that's mean curvature. And now flow by mean curvature couldn't be simpler, more simply stated than this. It's just saying that the normal velocity by which your surface moves is equal to up to the sine, the mean curvature. So that typically has a smoothing effect, which you see, for instance, in a linearization. That means if you would have a kind of a corrugated surface, as indicated here, it would make the surface smoother, the corrugation would slowly go away. But then in the large, if you're far away from planar situation, singularities actually may occur. And this starting shape, which I mentioned here, if it's a little bit more extreme, it's not hard to imagine that that you will have something like a pinch-off. At a specific time, you have a singularity, then these two ends separate and go on shrinking as spheres. So it's from a mathematical or from a differential geometry point of view or PDE point of view, it's something very natural. It's something like the standard geometric heat equation or standard parabolic equation. It's the standard thing on the extrinsic level. If you think in terms of extrinsic curvature, mean curvature is a kind of an extrinsic curvature, as opposed to kind of its the intrinsic heat flow, which would be the Ricci flow, which is also well studied geometric evolution equation. Okay, so that's one slide about what mean curvature flow is. And there is one feature of mean curvature flow which makes it kind of very valuable as a modeling tool in physics and more particularly in material science, because as some of you I'm sure will know, the mean curvature has the interpretation of being a first variation of the surface area. So it tells you that how much you increase or decrease the surface area as you move to a parallel surface on one or the other side of the surface. And as a consequence of this interpretation or identification of mean curvature as the first variation of the surface area, you realize that mean curvature flow, and that's kind of the global version of its local smoothing property, always reduces the surface area. So if you compute the time derivative of the surface area of sigma, you find a negative number or a non-positive number, which you could either write as the integral over the normal derivative, so normal velocity, or the integral over the mean curvature. So, so mean curvature is, flow by mean curvature has always this property that it decreases the surface area built-in. And that makes it interesting for modeling in physics because interfacial, I mean the total surface area can be assimilated to interfacial energy. So for instance, and that's the important example I will stay with, think of a polycrystal, so a metal which is not a single crystal, but which is made out of different grains, typically many grains, where the lattice type is the same, but the lattice orientation is different. And then it's kind of, even if you don't know much about physics, it's not difficult to understand that the surface that separates two grains carries something like an extra energy, like an interfacial energy. And therefore, mean curvature flow, in fact, was probably introduced in material science by Mullins, another CMU faculty member in engineering, who kind of postulated this as a good model or used it as a good model for the aging of polycrystals. So the reduction of this surface area of this interfacial energy by what's called the diffusion-less phase transformation, where kind of near the boundary, the lattice reorients. And but then if you think about this, you come to the kind of the next step, namely that when you think of a polycrystalline material, it has many grains. So it's not just an inside and an outside. It's not just a single surface that separates an inside from an outside, but you have many surfaces, and they typically meet at what's called a triple junction. So in 3 dimensions, that would be something which has which is one-dimensional. In 2 dimensions, like here, it's a point. And there should be some additional information given on what the motion does at these so-called triple junctions. And that's the so-called Herring angle condition, which tells you that at such triple junctions, there should be a local balance of the surface tension. So think of kind of each of these surfaces pulling in different directions in agreement with the strength of the surface tension. And then there will be some kind of equilibrium, some kind of 3 equilibrium angles, which would be 120 degrees if the surface tensions were all the same, but which could be different if the interfacial energies were different, depending on whether you're here or here. So that's the additional element which you have. But then you realize that such an extension of mean curvature flow, such a multi-phase mean curvature flow, has other types of singularities than this dumbbell pinch-off singularity I showed you on the first slide. And in some sense, they're much more generic. For instance, what will typically happen is as the interface between the grains moves by mean curvature, neighboring relations will change. So for instance, it will typically happen that, like indicated in this little picture here, that while before some time, grains 1 and 3 were neighbors and 4 and 2 were not, after some time, there is kind of a singular event where this changes. And then what will also happen is that grains vanish. So here's another cartoon of such a situation where initially locally you have 4 grains, 1, 2, and 3 surrounding grain 4, and after some time this grain is gone. So in fact, this dynamic, this relaxational dynamic, as a combined effect leads to a coarsening of the grain configuration. So the fact that due to a combination of all of these mechanisms, the number of grains decreases, the typical size of the grains increases, so therefore coarsening. And that's a topic which I learned from David Kinderlehrer, the chair, when I was at CMU as a postdoc, and he's one, but there are many people who are kind of thinking from this from an applied math point of view. It is a fascinating area to understand the statistics, and of course also very important for material science to understand the statistics of this type of grain growth. Okay, so now I told you about, at least very briefly, what mean curvature flow is, what multi-phase mean curvature flow is, and how it's used in material science in the context of grain growth. And now I want to kind of say a couple of words or a couple of slides on kind of the pure ideas which will play a role in this talk. And that has to do with gradient flows, because mean curvature flow, I use the abbreviation MCF, is not just any dynamics that reduces the total surface area. In fact, it's more intimately related to the total surface area in the sense that it can be completely formally interpreted, so meaning non-rigorously, interpreted as a gradient flow of the total surface area. So, so the dynamics that the nominal velocity is equal to minus the mean curvature can be interpreted in the sense that the configuration evolves according to the negative gradient in a suitable sense of the surface area. And so even despite the fact that this is something that cannot or is difficult to make completely rigorous, it helps a lot in thinking about dynamics, because you can picture an energy landscape, kind of an infinite dimensional energy landscape, which is kind of the set of all your possible configurations, geometric grain arrangements, boundaries, and you perform something like a steepest descent in this energy landscape. And as you know, in order to make sense even of the word steepest descent, you have to know what's steep and what's shallow. So in order to make sense of a gradient flow, it's not just enough to have the vertical axis, to have units on the vertical axis, which are given by the energy here, the interfacial energy or the total surface area, but you also need to have units or be able to measure distances on configuration space. So in a certain sense, you need something like a Riemannian structure, or at least a metric on configuration space to think in terms of gradient flow and think in terms of energy landscapes. And now there is one problem with mean curvature flow, which is the following. So in differential geometry, how would we kind of measure the distance between two configurations? Let me call them sigma 0 and sigma 1, because I'm thinking of surfaces. So configuration space is infinite dimensional. Well, you would look at all connecting curves, which are now curves of surfaces, and you would look at the energy in the sense of differential geometry, at the energy of such a curve of configurations, and you would minimize, which is kind of the speed, which here is the normal velocity, and you would minimize over all possible connecting curves. So that would be the right kind of geometry to put here on configuration space to make mean curvature flow a gradient flow of the surface area. Now that looks, of course, very fishy, and it's even more fishy even more suspicious than you would think, because there is a nice and very intuitive argument by Micho and Mumford that this distance actually degenerates. It's always 0. You can kind of connect the boundaries of two sets by curves so that this energy becomes as small as you wish. So that already tells you that it's a little bit kind of, on the one hand, it might give you the right ideas, but this one is shaky. So, but let's not worry about this for a moment, and let's turn to the Giorgi, because the Giorgi said, or kind of worked out, that any gradient flow has kind of something like a natural time discretization, which comes in form of a sequence of variational problems, and you call that minimizing movements. So the important thing is that this only appeals to rather robust quantities, no differential structure in an explicit way. So let's assume you just have not really a Riemannian manifold, but just a metric space, and you have a function on that space. And because I have characteristic functions and set in mind, I will denote typical points of that manifold by chi. And now the Giorgi's minimizing movement scheme takes on the following simple form. You give yourself a time step size h, and now you define kind of a sequence of configurations. You update your configuration in the following way. At the nth time step, you minimize the energy plus the squared distance to the previous time step. So you don't right away jump to the minimizer, but you stay close to the previous time step, and in fact, you stay very close to the previous time step, because you put a huge factor in front of it, 1/2h. H is the time step size. Think of it as being small. So this is a huge number. So you just move a little bit closer to the minimizer, or towards the minimum of the energy. So here is kind of the rendering. And it's very easy to see that if this metric structure really comes from a Euclidean structure, if that's a Euclidean structure, and E is smooth and everything is finite dimensional, then the scheme here is nothing else than the implicit Euler discretization of the gradient flow dynamics. So it's a way of kind of endowing gradient flow dynamics with a natural time discretization, which comes in form of a sequence of variational problems, and the Giorgi called this minimizing movements. And the paper which David alluded to was a paper where, in a certain sense, a minimizing movement scheme for a Wasserstein metric was written down and connected to nonlinear or linear diffusion, to the Fokker-Planck equation in this case. So, but the idea of minimizing movements is older. So, so here again is the minimizing movement, the abstract minimizing movement scheme, and now from a numerical point of view, it looks very nice because you immediately get a good estimate by comparing your minimizer with the previous time step. So you just say, well, whatever value of this functional is in the minimizer, it couldn't be more than the value which you get when you plug in the previous time step, in which case this term drops out and you're just left with the energy at the previous time step. So it's clear that this discretization is stable in the sense that it always decreases the energy. It's sure, guaranteed to increase the energy. And in fact, if you use these inequalities and you sum them up, there is a bit of telescoping, and you get this, this type of easy a priori estimate, where you can always control not only the energy at a later time step by the initial energy, but you can also control the sum of the squares of the distances properly scaled with h. And this almost looks like what you would expect for the continuum dynamics, which is the energy identity which you have for a gradient flow, which would tell you that the energy of the final state plus kind of the energy of the curve is less than the energy of the initial state. But then you realize, oops, you're missing a factor of 1/2. And then first you may think, okay, perhaps I didn't do the calculation correctly, but then you realize, no, you did everything correctly, but still you're missing this factor of 1/2. And the Giorgi's idea are essentially can be very loosely summarized by saying what you have to do in order not to miss this factor of 1/2 and to get the right dissipation relation, the right energy inequality, at least in the limit. Right? That's his contribution, and he introduced two abstract notions: the variational interpolation and the metric slope, which I want to explain on one slide because they're beautiful and they work and they will actually serve us, but that will only become apparent at the end of the talk. So just give me indulge, and and let's look at the at these two tools. So what the Giorgi said is, okay, so eventually you want to kind of compare this time discrete scheme, which he considered kind of in this very abstract framework, eventually with a continuum solution, with a continuum trajectory. And so that means you have to interpolate in time. And of course there is kind of the poor man's version of interpolating in time, just piecewise constant, as indicated here by this view graph. And now you may say, okay, but piecewise linear in time is much better. It looks smoother. But remember that there is no natural linear structure, right? I mean, M is just a metric space. So at least if I play the game that I don't want to assume more than the Giorgi, that doesn't mean anything, saying I want to interpolate linearly. But nevertheless, just with the tools at hand, which you have, kind of the metric and the energy functional, there is a way of continuously interpolating by using the variational problem itself. So the idea is very intriguing and simple. You go to kind of the time at the previous time step, which is n-1 times h being the time step size, and you want to define it for plus s, where s is somewhere between in the small time interval from 0 to h. And what you do, you just say, well, that's supposed to minimize this variation problem, which exactly has the same shape as the one before, just that I'm playing around with this prefactor. If s is close to 0, this term is tremendous is overwhelming and forces me to be close to chi-n minus 1. And if fs is equal to h, then I get the same variational problem as before. So I should get something that, morally speaking, continuously interpolates the two things. That's the first idea. The second idea is, well, eventually I want to connect to a gradient because I'm interested in gradient flows, but again, if you want to play the game, I don't have a gradient, right? I don't have a differentiable structure, so I cannot make sense of it. But nevertheless, even on a metric space, you can kind of give a meaning to the slope of a function. So in a certain sense, to the size of the gradient, just by looking at difference quotients and looking at the limit where your test configuration moves closer and closer to the limiting configuration. So that's the idea. Those are the two abstract ideas, the variational interpolation and the metric slope. And now the wonderful observation by Giorgi was that with these tools, you could kind of regain the missing term, the factor 1/2. So instead of just having the black and the green, it gives you in addition the the blue term, which involves the metric slope and which involves the variational interpolation. And he designed these tools because he thought this was now, or he hoped, and there is hope, reason to, that this is now a good tool to pass to the limit, to study convergence of the scheme, because in a certain sense, you have the feeling that just by soft lower semi-continuity arguments, you should be able to relate this metric term to the limiting term here and this energetic, this gradient term to this term in the limit, which is the square of the gradient in whatever Riemannian metric you have. So you should be able to pass from this inequality to this inequality by soft lower semi-continuity arguments. And this inequality, in fact, is equivalent, at least formally equivalent, to the gradient flow structure. So I think that was the philosophy, one of the philosophies of Giorgi here, that these tools serve to get kind of a good, robust general convergence theory. And these ideas have been taken up, formalized, and applied, beginning by the work of Etienne Sandier and Silvia Serfati. But then there's also recent, this goes on, long list, there's recent work which I find quite interesting by the Eindhoven-Berlin group, where they say sometimes in homogenization problems, it might be more complicated. There might be some kind of interaction between the two terms. So this is an active area, kind of understanding singular perturbations, limits within gradient flows. Okay, we'll get back to this. Now the main object is really this numerical scheme, this extremely appealing numerical scheme, which was introduced already also a while ago by Merriman, Benson, Osher. And it's a very practical computational scheme for motion by mean curvature flow. And it's amazing by its simplicity. So I can just explain it in one line. So you give yourself a time step size h, and you describe your sets, and therefore also the boundary of your sets, by the characteristic function of the interior. So chi, you should always think of chi as being a characteristic function of a set omega, and you're interested in its boundary sigma. And so how does one time step of the scheme proceed? Well, you take such a characteristic function at the previous time step, you convolve it with the heat kernel, so the Gaussian at time h, which means in a certain sense you solve the heat equation for a little time interval h. Then you get a function here indicated in red that's no longer obviously a characteristic function, it's smooth, and it has values strictly between 0 and 1. And then you do a thresholding step. You just ask the question, where is this function larger than 1/2? And where is the function less than 1/2? And that defines your new characteristic function and thereby a new set. And there you go. You have started with a set, you get a set. And that supposedly is mean curvature flow. So indeed it is. So here is again the scheme. So let's look again now just in 2 dimensions at our dumbbell shape. So that's the characteristic function of that shape at time step n-1. Now you convolve it with a Gaussian, so the picture gets blurry, you get grayscales. You seek for the level set 1/2, and that gives you the new set, the new peanut. And if you look closely, the neck will have moved out a bit, and perhaps these things will have shrunken a bit, and that's perfectly what should happen, because if you place yourself in a point on the equator of the neck, and you take the convolution, which is kind of an average with respect to radially symmetric function, you will see more black than white. So the value at this point will be definitely larger than 1/2, which means after one time step, this point will be inside the set. And at this region, exactly the opposite happens. So it looks very convincing that this should go the right direction. And now this is just a time discretization. Of course, you also discretize it in space by, let's say, a regular grid. And then the most expensive step is the convolution step, but then you can carry that out by fast Fourier transform. And so that makes it a very easy, intuitive, and powerful scheme for mean curvature flow. And not surprisingly, people, I mean, analysts, and here you have kind of a number of famous analysts, have immediately jumped on this scheme and tried to understand its convergence. And there's one thing you can easily realize, that this numerical scheme preserves one of the key features of mean curvature flow, which is a comparison principle. So the comparison principle of mean curvature flow is, if you start with 2 sets which are nested, and then the boundary evolves, the 2 boundaries evolved by mean curvature, this nestedness is always preserved. So it's kind of a maximum comparison principle. And it's clear that the scheme preserves this property because convolving with a non-negative function doesn't destroy the ordering, and going to less sub-level sets doesn't destroy the ordering. So the experts know that this is the entry point for the notion of viscosity solution, because that's kind of a very powerful notion of solution for first and second order elliptic and parabolic differential equations and geometric motions, which is extremely robust and allows to essentially by soft methods to show convergence of the scheme to mean curvature flow in the sense of viscosity solutions, which is a very nice result, not completely satisfactory because the experts will know there is fattening and so, but still it's one of kind of the successes of the scheme that there is a convergence proof in the 2-phase case. In the multi-phase case, the scheme literally works the same. So it's just that now instead of having one characteristic function and its complement, you have n characteristic functions, one for each phase. The characteristic functions have to sum up to 1, no vacuum, everything is covered, no overlap. But then you do exactly the same. Component-wise, you convolve your characteristic functions, and then you ask which of the n characteristic functions is the largest. And here is numerical simulations of Tim Lauk's, kind of where the 3 phases are represented by 3 different colors. So here you have the 3 characteristic functions. Now you convolve, that picture gets blurry, and now you sharpen again by asking where is green dominant, where is blue dominant, where is red dominant, and you do that, and that's a multi-phase evolution by mean curvature. And in fact, you already see that the Herring angle condition, the fact that in this case you should have the same angles in each sector, is already kind of is already there after one time step, even if your initial data didn't have that property. And, but okay, that's just a little game, but Matt Elsey was a PhD student with Selim Izedoglu and Peter Smirka, showed that this can be carried out in 3 space dimensions with more than 100,000 grains. So it's really, I mean, they showed that this scheme is able to really go in an area where you can extract statistics. I mean, of course, there are much more numerical simulations, but that's one which I find really impressive. On the theoretical side, there's much less known about kind of the multi-phase mean curvature flow. Only fairly recently, there was kind of a long time existence result by Kim and Tonegawa with respect to a different weak notion of solution named after Ken Bracke. They're interesting, you know, by some of the top geometers here. You will see some of the names, interesting analysis of networks. So that's the 2D version where strong solutions past singularities are considered. So that's also from the analysis point an active area. So now, in a certain sense, what did we do? In a certain sense, we asked 2 questions. The first question is an applied question, and is the following: how can you? So there is this kind of very performant multi-phase version of mean curvature flow, which can be applied to simulate grain growth. But when you have grain growth, and I'll go into a bit more detail later on, it's not right to assume that the surface tensions are all the same. In fact, at least you should be able to, for every pair of grains, be able to pick a different surface tension. So if you have 4 grains, you should allow for 6. So 4 choose 2. I'm not sure about my numerology. For a large number of different surface tensions, and that was the first question we addressed. How can you kind of generalize the scheme without losing its simplicity and its low complexity to such a situation? And experts will know that you should also think about mobilities, and that was very nicely solved, much nicer than we originally did by Selim and a student, I guess. And that's the first thing I want to briefly talk about. And the second thing is, okay, can we also get convergence in the multi-phase case? And now comes kind of the thing which connects the different strands of my talk, is that both answers to these questions are based on a minimizing movement interpretation of thresholding. So that came a bit as a surprise that this thresholding scheme, which is extremely natural from the point of view of the comparison principle for mean curvature flow, is also extremely natural from the point of view of gradient flow structure of the mean curvature of mean curvature flow, in the sense that it can be interpreted in the Giorgi's spirit as a minimizing movement scheme for mean curvature flow. So let me try to explain that. So let's look at the 2-phase case. So thresholding written in a very compact way means kind of convolving your previous time step and looking where it's larger than 1/2. And in fact, this is a minimizer of a functional which has the algebraic structure of a first term which can be interpreted as a squared distance of your functional which you minimize to the previous time step, plus something which should be interpreted as an energy. So that's an extremely simple observation. It's just a consequence of simple linear algebra that this functional, just using the symmetry of the heat kernel, can be rewritten in such a way that you can read off that its minimizer must have this form. So it's I mean, there's nothing behind it from an analytic point of view. It's just an extremely simple observation, but an important one. So here again is the functional. So thresholding, what comes out of the thresholding scheme, can be interpreted as the minimizer of variation problem. Let me stress that this is not at all how you would do it numerically, right? I mean, thresholding is perfect as a numerical scheme. It's just an interpretation. It's just an interpretation. And now, what's the link to mean curvature flow? Well, if you look at what's supposed to be the energy in the sense of the Giorgi, indeed, it looks like the surface energy, because it's the product of the complement with the convolution of what's inside. So here you have 1 minus chi, you have chi. You convolve the chi, you get the red curve, and you look how much of the red curve, how much of the red spills into the complement. That will be something which spills out over distance square root of h, because that's the length scale of the heat kernel by parabolic scaling. So therefore, if you normalize it by 1 over square root of h, it's very intuitive that this should be close to C0, which in fact is 1 over square root of pi, times the surface area of the interface. And a very elementary heuristic consideration of similar type tells you that this expression here, which you should assimilate as 1 over h squared times 1 over h squared, 1 over h distance squared to the previous time step, indeed behaves like this, in the sense that if you write your current configuration as a graph over your previous configuration in terms of something which you might assimilate with a normal velocity, then this here gives exactly v squared, which should be the right expression for mean curvature flow. Okay, so and this extends to the multi-phase case, when all the surface tensions are easy. In this case, your energy functional is just kind of, you look at every pair of phases and you look at this heat content, if you want, this spilling, and it's known that this gamma converges to the right total interfacial energy. And there is the analog of the squared distance term, and thresholding, indeed also the multi-phase case, is minimizing the same thing. Okay, so two-phase, multi-phase, same surface energy can be understood in this variational thing. So far we haven't gained anything, but now that gave us the right idea how to generalize to more general interfacial energies. And the idea is just put them here, right? I mean, this is the interfacial energy between the I and the J phase. So put the sigma ij there. So let's do reverse engineering. Let's put the sigma ij there. And then we still know that this, as it naively should be, gamma converges to kind of the right total interfacial energy, now weighted with the appropriate surface tensions. We take the same squared distance as before, and then we say, okay, now let's look at the minimizing movement scheme. Let's look at the minimizers of this distance square to the previous time step plus the energy. And surprisingly, that's again a thresholding algorithm where you convolve and you look who is largest. The only difference is that there is a sigma ij here. So it has exactly the same complexity. So just by reverse engineering, we uncovered the right way to put the interfacial energies here. And perhaps, you know, certainly people could have done that earlier, but people have tried. I mean, there are some attempts of introducing different interfacial energies into thresholding, which had kind of a completely local perspective and were probably not, are not as performant as this one. And this came from this minimizing movement perspective. Let me quickly talk about, because that's kind of interesting, of how what the assumptions on the surface tensions are. So there's one very natural physical assumption on the surface tensions, which is the triangle inequality. So the sum of two shouldn't be larger than one of them. And the picture you should have in mind in real space and configuration space is that if that were violated, then in a certain sense, the third phase should wet the two others, and you should, if it were violated, you should pass to a relaxed function. But then we need a second ingredient, which is, I guess I'm afraid to say, not really physical, but which we need for the scheme to be a proper minimizing movement scheme. We need that the matrix, which is formed by the surface tensions, is negative definite if we restrict it to the hyperplane. And that has an interesting kind of convex analysis interpretation. If you think of your surface tensions as being kind of length in an abstract metric space between kind of which just contains n points, n being the number of phases, then the triangle inequality, the benign triangle inequality in a certain sense, means that this metric space can be embedded into the L infinity metric of high dimensional Euclidean space. This condition is also related to an embeddability, namely the embeddability of the square roots into L2. And the strongest condition is if you had L1 embeddability, which you always have when you have less than 5 phases, in which case one could also do a different and easy treatment. So there is this blue condition, which we need. So we did ask Selim Esedoglu and I, is it satisfied for the application grain growth? So although this is a 2D picture, we were thinking of a 3D case. So what's kind of, we were looking at kind of the most common grain boundary model, which has kind of a little bit of symmetry and a little bit of physics in it. So the symmetry is that, okay, so every grain has a different lattice orientation. Let's think of a cubic lattice. What's relevant, and that's the first symmetry restriction, is the angle between the rotations, or the, of this, the relative rotation. You should look at the angle, and then you should factor out symmetry of the lattice, meaning you should look at the minimum over the octahedral group, the symmetry group of the cube. And that's the right way to kind of think of an angle between two neighboring orientations. And then there is a right physics, which is how does the energy depend on the angle? And because people have kind of the idea that grain boundaries are made out of kind of dislocations, individual dislocations which concentrate, there should in fact be some logarithmic dependence of the energy on the angle. So there's an infinite slope at the beginning and then it saturates. In fact, there's nice work by Luckhaus and Lautieri who derived that more rigorously. And this standard model satisfies both conditions. Triangle inequality, that's easy, and this negative semi-definiteness is where we have to use a little bit of elementary representation theory. Okay, so how much time do I still have? 5 minutes, 10 minutes? What's the...
David, you're muted.
Yeah, I see. Okay, I'm unmuted. So you have about 13 minutes, certainly 10 minutes.
Okay. So that was kind of the interesting insight from the applied point of view, which grew out of this minimizing movements interpretation of thresholding. Now let me talk about, that's more analysis, about how it leads to kind of a convergence proof, at least a conditional convergence proof. So I will state it we prove it, so that's work with Tim Laux. We prove it for any number of phases, provided the surface tensions satisfy the strict triangle inequality and are negative definite. But I will state the result here so that it's more digestible and fits on a slide just for the two-phase case, where here I recall what the energy is. And so we give ourselves an initial configuration which has uniformly bounded energy, which essentially means that the interfacial length has to be finite. We then run the thresholding scheme. So we use the BMO scheme, which is, as I described, a priori not variational, but very easy. We look at the piecewise constant interpolation, and we want to argue that this converges to mean curvature flow. And in fact, we have three convergence results. The first one, which is the oldest one, was the hardest towards what's called a BV solution. And then we became more and more softer and proved convergence to Brachet solution. And then in the end, that's the most recent stuff, to a Giorgi solution. But all of these results are conditional. I will explain that a little bit. But before doing this, let me just, so this is a slide which probably for those who haven't seen that before is a bit hard to decipher. For those who know a little bit of geometric measure theory, it's probably very easy. It's just to say that since we're interested in kind of convergence results past singularities, we can't really work in the smooth setting. So we have to look at kind of robust, weaker notions of mean curvature flow. And there is one with help of geometric measure theory where you say there's a robust notion for the surface area of a set, which is given by the total variation, which connects to functions of bounded variations. There's a robust notion of a normal, which has to do with polar factorization of measures. There's a robust notion of a normal velocity, which is just distributional. And there is also a robust notion of mean curvature, which is also distributional and uses kind of integration by parts on the surface with the tangential divergence. So we'll appeal to these notions. And here is the first result with Tim Laux, which essentially tells us that indeed we're converging to a solution of mean curvature flow in this weak sense. In this weak sense, the mean curvature is equal to, or the normal velocity is equal up to a factor of 2, which is in here because of different normalization to mean curvature. But there is a caveat, namely we have to assume that energies converge. So it's not just enough to assume, which we would get by soft compactness, that we're on a subsequence where we have convergence of the sets in the sense of L1. We also need convergence of the perimeters in this sense. And so let me talk a little bit about this, because that connects to something which is also interesting from a historical point of view. So here again is this additional convergence assumption, which we have to make in order to connect to mean curvature flow. And incident, so what I want to tell, the little story I want to tell, and then I'm almost at the end, is that this is exactly the same assumption which my PhD advisor, former PhD advisor, Stefan Luckhaus, with a kind of a PhD student who did his PhD at the same time as I, used to prove convergence of another time discretization of mean curvature flow to mean curvature flow. Exactly the same notion of solution, exactly the same, morally the same assumption. But that was kind of a time discretization of mean curvature flow, which didn't come from scientific computing, but which came from geometric analysis. So it's the famous Angren-Taylor-Wang minimizing movement scheme. And let me briefly tell you about it, because it's an interesting scheme. So here I recall again the general structure of a minimizing movement scheme: energy plus squared distance to the previous time step, strongly penalized by the time step size. And what Rob Angren, Jean Taylor, and Li Wang kind of postulated, the scheme they proposed is the following. So let's take the surface energy, as we should for mean curvature flow, and let's take this type of distance between the current set and the previous set. So you take the distance in RD, in your three-dimensional space, distance function, and you integrate it over the symmetric distance between the two bulky sets. So that, in a certain sense, was a minimizing movement scheme avant la lettre. So I think they came up with this before the Giorgi kind of coined his abstract theory, and it might very well be that there was some inspiration. And so that's the scheme on which Luckhaus and Sturzenegger worked, which is a bit more of an academic scheme, but very influential. But it's not just academic. There is kind of interesting work by Antonin Chambol and Matteo Novaga, who kind of embed this into something that can be actually numerically treated. Okay, so last couple of slides. So we were dissatisfied with this result because it did not even give us the energy inequality. That doesn't come out of this weak notion of solution. And therefore, we wanted to kind of also connect to a notion of solution which has the energy inequality, so to say, built in. We had two choices: Bracke's notion of solution, and I won't talk about this because of lack of time, and the Giorgi inequality, which I mentioned in the beginning. And that's, so I'm jumping over this. That's exactly, now I'm coming back to this one slide, which I had at the beginning. So we really now use kind of the tools of the Giorgi. We use the variational interpolation on the level of the BMO scheme of thresholding. We use the metric slope for the functional at hand. There should be an index H here. So we have, by Giorgi's theory, which we found in the book of Ambrosio Gili Savary, we have this inequality here, and we can pass to the limit in this inequality essentially by mostly soft lower semi-continuity arguments, recovering this limiting inequality, which is a weak form of mean curvature flow. So that's this last theorem, which makes the connection between these tools by De Giorgi and the thresholding algorithm of Merriman, Benson, Osher, and Benz, Merriman, and Osher, and I think I should stop here. Just there was a little bit of the proof last slide, so this was a bit of a kind of fairly broad, but of course superficial combination of a bit of geometric analysis, a bit of material science, analysis on metric spaces, but in the end motivated by scientific computing. Okay, let me stop here, and thanks for your attention.
Thank you, Felix, for a beautiful talk. If there are questions, perhaps you can, I see there are some in the Q&A, and perhaps Felix can just respond directly.
So Q&A, okay. There's one question. These minimizing movements look like proximal steps in optimization, right? So I'm not really sure about their definition, but my gut feeling, the answer would be yes, that's the same. But I would say the philosophy is different, because we're not setting the scheme up to find efficiently a minimizer. But we're, the interest is in the dynamics. So it's not minimizing movements. Minimizing movements are not designed to, they don't claim to be a good scheme to get to the minimizer. They claim to be a good discretization of the gradient dynamics. So that's, I think, a different spirit. But I think mathematically, the strict answer is probably yes, unless I'm saying something stupid. So the second, so should I read the questions?
Yes, why don't you do that?
Okay. So the second question by Keith Promislov is, is it known if there are extensions of the minimizing movement techniques that elegantly encode a normal velocity that includes surface Laplacian of a mean curvature or other elements of a well-more normal velocity? So probably Irene would be somebody who could answer that question. So in principle, I mean, since many of these higher order, like surface diffusion, has the structure of a gradient flow, it's can be understood as the gradient flow of the interfacial energy with respect not the L2 but the H-1 inner product on the surface. In principle, the mathematical structure is there. It's not clear to me whether there is a good characterization of the distance in the large. There is in case of Mount Sekerka, which is kind of the third order counterpart, but that question should be, I think it should be answered by other people. I think there are certainly approaches to existence results for higher order geometric motions via minimizing movement ideas. Sorry, I can't give a better answer. Sorry. So Raghav Venkatraman writes, is the energy convergence satisfied in the multiphase case when neighbors are exchanged or islands collapsed? So yes, the danger for the danger for the energy convergence is even present in the two-phase case when two components of your inner phase kind of in the limit would touch along kind of a straight interface. Then there would be that's conceivable, and there would be a loss of energy, which in this case you would hope to overcome by not using a BV descriptions but a very full description. And so there's no. So in principle, there certainly is room for improvement of getting rid of this condition by moving to kind of better notions of solution. Okay. And what about boundary conditions? So same person, what about boundary conditions? Do the convergence results you have tell you how the interface energy meets the boundary? That's a very good question. So, I mean, in all our convergence results, we cheated because we put ourselves on the torus. I think Neumann boundary conditions, so natural boundary conditions, I don't think that there is a problem with the convergence results. How would you, because that can be well kind of encoded if you have special wetting conditions, so that certain phases like to wet the boundary, then of course you would have to add energy terms. How this is, that's not so clear to me how this is implemented on the level of the thresholding dynamics, but I wouldn't be surprised if people have thought in that direction. We cheated in the sense that we completely ignored, I mean, by going to the torus, we ignored that interesting question. So I think that's it in terms of questions.
Okay. Perhaps we can thank Professor Otto again for a remarkably beautiful talk. I won't make noise. And so this session is then closed.
Thank you very much for your attention. Thanks, David, for sharing it.
Oh, Felix, wonderful to see you.
Bye-bye.